Right. So, as per our traditional last lecture for the day is a tutorial. So we are very happy to have Sato from Jefferson Lab, who's going to teach us about usage of AI and ML methods for inverse problems.
Right. Okay, thank you, Alexei. And thanks for the organizers for inviting me. So we got 3 hours today, tomorrow, and the day after. And I was told to give a tutorial on AI ML. And this is a very challenging task because every time that you read about it, everything changes. And so I didn't know what was the best idea here. So before I go into the meat, let me. Or there's an button on the side. It is on. Maybe I need to click. Yeah. Okay. I put this slide that you can also find. There is these are recent workshops in this area of AI/ML, particularly for EIC science. 3 years ago, more or less. These applications are much more broader than EIC science. It includes more stuff in nuclear physics, stuff like quantum state representations of using neural nets, which are very popular, as well as solving inverse problems, and all the way, to maybe the most recent workshop that I attended was a poetic meeting in relation with EIC. And yeah, so you can check it out. These links, there are interesting talks, and this area is fascinating. There's a lot of appetite, also from funding agencies to sort of kind of utilizing AI ML for science. So anyway, if you have any question, just reach me out. Okay, so as I said, I really didn't have a really good plan for you guys, and I thought, what should I be talking about? And since I don't know much about the audience, I want to maybe start with some fresh recap about neural nets and how to use it with Torch. If you haven't never used Torch, if you have never used this would be a great starting point to play around. I will give you some examples to play with. We will go very basic, so feel free to ask questions, entertain ourselves for an hour for the time being. And then I don't know if the time will allow me, today to go all the way to generative AI. I'm going to be talking about normalizing flows. And what we're going to do as a tutorial is to implement that thing from scratch because it's pretty simple. And the reason that I wanted to emphasize on that is that I truly believe that, as Ernst was saying today, have you ever fit a line? You might have like a minute, software or list quest to fit a line. I think that having a normalizing flow should be already in our pocket, or everyone's pocket, to actually address any questions about reconstructing physics from observational data relevant for EIC. So I thought that for the purpose of tutorial, maybe just in depth, trying to polish in that skill of normalizing flow was a good idea. And then maybe by the end of this 3-hour session, I will try to sort of connect a little bit more with how this can be connected with Hadron structure. All right. So we are going to be spending time coding. Can anyone you here have ever used Colab, or have you raised a hand who has not used Colab? There is one person. No shame on that. Do you have a Gmail account? No. Okay. Well, start creating a Gmail account. I don't really know if you can access Colab without Gmail. Try it out, and then I will, we'll see how it happens. Also, if you don't have a laptop, although it seems if not the case, just pair up with, with your person next to you. So this symbol means whenever this symbol occurs in slide, it means that you have to put your hands there and I'm going to stop talking. And that's my great way to get a little of time. Okay, so to get started, I suggest everyone to fire up your Google Colab, to make sure that you have access to Google Colab. If you go to Google Colab, you surely see something like that. I'll give you a minute to make sure that you have Google Colab fired up. I'm going to count my minute. By the way, if you have like either your own Python notebook in your laptop, also that works. You need to have PyTorch installed. That's the bare minimum. Otherwise, just use Colab. There is nothing fancy that I'm going to be showing. Anyone having issue? Has anyone hasn't been able to get to this point? One person. All right. So it seems like everyone else is ready to go. All right. There is this runtime thing here that you will have to, you don't have to do it right now, to select a GPU because you doing machine learning without GPU is a little bit sad for good reason. So I suggest to maybe pick it up this one. But for the purpose of now, you can use CPU, it doesn't matter. But you can see that from the runtime, you'll be able to get a GPU hardware. All right. Also, because we will use a bunch of things from Torch and Matplotlib to make plots and whatnot. This is not an image. This is text that you can go into my talk. You can literally copy and paste this stuff and put it here. Shift Enter, and then you should be able to at least get the headers kind of ready, for the tutorial. I tested yesterday and it worked. Let me know if it doesn't work. There is an error, I should be able to troubleshoot that. Give you 10 seconds. All good? Anyone with any trouble? Yeah.
It's still running.
It's still running. Okay, that's okay. Because you're using for free. Price of using free. But you should get the what I hope is that it doesn't throw any errors. That's the bare minimum. Okay. Anyone else all good? Can move on. All right. All right. So to do machine learning, we start again with neural nets. So let's start sort of diving into neural nets, some very basic things. I always kind of get bored whenever I see this. But what is interesting is that whenever I ask someone, like even my collaborators, about explain to me a neural net, they seem to have a trouble explaining to me, and they seem to think that it's just points connecting with lines. So I'm just going to try to give you my simple perspective of what a neural net is as it is. It's kind of non-standard, okay? So let me show you first an equation. Right.
Yeah.
Can someone tell me what is the name of this equation? Anyone?
It's a system of linear equations.
It's a linear equation, right? That's it. Nothing sophisticated. So this is, let me see if I did my homework. No, I did my homework. So this is a vector, okay? This is a vector. This is a matrix. And this is another vector. That's it, as simple as that. Now, one thing, okay, and we have to talk about some names. So these guys are called input features. And these guys goes under the name of output features. Simple. This is called a weight matrix. And this is called the biases. Okay? Now, normally, when you go to school, people will tell you that this matrix normally is a square matrix. And this is where you play most of the time with square matrices because it has nice properties. For the purpose of neural nets, this doesn't have to be a square matrix. That means the dimension of the input features and the dimension of the output feature doesn't have to be the same. Okay, so we're going to relax that condition in this context of this. And I would argue that if you understand this equation, you're already understood a neural net because that's essentially the backbone of a neural net. All right, so this is a simple example. I have two features, two output features, four input features. My matrix cannot be a square. It has to be 2 by 4, right? And my bias vector has to be 2 so that I can match with here. So the ordinary product of matrix and vector holds. So the question is, in this equation, how many free parameters you have? You should be able to count them right away. It has to be 10, right? So it's 2 by 4 plus 2, that's 10. You're done. So essentially, this model, this is already a model. It's just a very simple linear model that has 10 parameters. Maybe a little bit more complicated than Ernst linear model, but it's still a model. All right. Didn't work. So the next ingredient to build a neural net is to put something called an activation function. And that sounds very, people will tell you about neurons and blah, blah, blah. I don't care. All you have to do is to have a function, for instance, that look like that. Maybe 0 below 0, and you start becoming a line. This is called rectified linear unit. There are other functions, arctangents, etc., that you can use. And all you have to do is to take the output from the linear layer and feed it into that function. So when you do that, let's try to see what's going on there. You start with 4, then it became 2, right? You feed this 2 into the activation function. This doesn't change the dimension. You're literally mapping this Y1 into a Z1. And then what you can do is you can feed this output into another linear layer. And so for instance, this time I'm going to go from 2 to 1, right? And so in this case, I will have yet another set of weight matrices and biases. In this case, I will have 6 new more parameters. And this is just a simple setup. And that's it. That's basically, to me, a neural net. Nothing more sophisticated than that. So in Torch, this linear layer is going to be written like this. And then linear 4 by 2. Why 4? Because we have 4 input features and we want to go from 4 to 2. What this guy does internally is to define a matrix that is 2 by 4 plus the bias. Sometimes, for whatever reason, you might want to eliminate the bias and you can put here an argument that says bias 0 or false. And that would eliminate these two guys if you wish, if you know what's going on. Okay? So this is how you write this linear layer. Then, in order to build past this thing, you just have to define a function like this. This is the activation function, the ReLU. I will get into a point why we have to use ReLU. And then after, you basically feed another linear layer that goes from 2 to 1. And if you want to go back to your fancy neural net cartoon, this looks more or less like that. So you have 4 features that ultimately go into 1. It is connected by these weights. All these lines are weights of the weight matrix. And you have also these external outputs, which are the biases. So that's sort of the graphical picture of a neural net. I really think that this is irrelevant. To me, when I'm working with this, I only see just these things. That's more interesting to me. Okay. What else I want to say? All right. So let's try to imagine how do we write this thing in PyTorch. And so there is this nice function called sequential. And you can actually put as many things you want here. So you start with the linear layer, 4 to 2. So that would be this guy. Then you have to say, what's the activation function? This case, I use tanh H. You can use tanh H. You can use really. What should we do to choose? Okay, that would be a question for you guys. Then we have also a linear layer, and we can keep stack on, on this layer. So when people talk about deep neural nets, what it means is that they have wrote a bunch of lines here. And then, okay, it becomes deeper. That's it. That's as much as it can get. There are other tricks in terms of optimization. There are things like, dropouts. There are things that you can actually add here. There are other types of layers that you can actually use. Famous things such as 2D convolutional layers that are very popular, or these days, the backbone of ChatGPT, which is transformer layers. So you can, in principle, do a lot of interesting tricks, but for the time being, to get started, let's just simplify it to be just this. So you can see just a linear transform followed by an activation function that maps into another space, and you get this. Okay. Yes.
Autocompletion. Just type model and then tab. Basically, autocomplete for you the whole cell. We'll try to autocomplete as it wants, but then can tab.
Definitely. By the way, no, this is an AI talk, so use any AI thing that helps you out to understand, okay? So as I promised, there's a symbol for collab. So let's do some quick exercise. And I have to, before you do that, I need to tell you two important features of how to use a model, okay? So this is technically a function. You should view that thing as a function that receives 4 inputs and outputs 1 output. However, there are 2 modalities in which you can use that function. The first modality is that you pass a torch tensor of size 4. You just literally feed it something like this. So this is a torch tensor of size 4. I just gave you an example. You feed it to the model, and it will give you a number, okay? You should test by yourself right now that doesn't crash, that this model will give you a scalar. The second modality is the multi-evaluation mode. So the idea here is, imagine that you don't have just only 1 row, but you have 3 rows, let's say, right? And you want to maybe feed all these things all at once to the model, just like here, to be able to get 3 outputs. So this row maps into this row maps into this, and so on. Try it out. It's important that you understand this distinction. Most of the time when I'm debugging, most of the complaints that I get is because I forgot what I'm doing. And so, you need to make sure that you know how to distinguish between these 2 setups. The model doesn't get projected into this mode or this mode. Internally, it understands to use this or this. You can also try out another thing, for instance, remove this entry here, just pass a 3 entries, and the model should give you an error. Right, that has to happen. Check it out. Okay. Let me give you a couple of seconds for you to renormalize with this slide. Yes, okay, good point. I made a mistake. So remove this thing here, okay? And it should work if you do that. Okay. Now, as I told you at the beginning, you can choose a GPU or a CPU usage, right? And so one of the things about Torch is that it allows you to explicitly operate on a GPU or a CPU. So how do you decide? How can you enforce that? You essentially send the model into a device. So in the headers at the beginning, let me go somewhere here. Yes, here. There is this thing here that I say I want at least one GPU, and I'm going to query if I have a GPU or not. If I have, give me the name of the GPU and store into device. Otherwise, it's a CPU. So if you have actually didn't select the GPU, the default will be CPU, right? Then it should have worked. So did you? The GPU. Right. So that means that then what happens is that this device was a GPU. And then when you go here, actually this error was a good thing to do. So you actually send this model to a GPU, but these guys are still on CPU. So in order to make these two things to work, you will have to append these two device here, two device, and then you can, inside of the tensor. So after the first parenthesis, dot device, two device, right? And then that means that this tensor of 4 is now on GPU, and then it can play with this guy. Otherwise, you have two devices as the error indicated. Yeah, it's sometimes annoying that something is in a GPU and CPU, but eventually you get the feeling how to use it. Right. Everyone good with this very simplistic example? You build the first neural net. Congratulations. You know how to use a little bit of machine learning. Yeah.
So what of these, I copied that, are the weights then?
What are what?
Like
These?
what of this code, I guess.
So this is a definition of a model, okay? Where I have the two linear transforms, and by construction, the weights and biases are initialized randomly.
It's just a random?
Yeah, random assignments. There is some Torch does something like the values of the weights and biases are proportional to 1 over the number of parameters that you have. But essentially, it's a random instantiation. If you re-instantiate this model and evaluate this, you have to get different outputs. That has to happen. So think about this, something like a sine of AX, where A was chosen randomly. Right. Nothing that useful, but it is your first neural net. Okay. Any other questions? All good?
What does the hyperbolic tangent do exactly? I mean,
I get what it does mathematically, but what's the point of this extra step, I guess?
To introduce non-linearities.
Okay.
Otherwise, everything will be
Yeah.
linear.
Yeah.
That's essential. But there is a theorem that tells that is in principle a universal approximator because of the non-linearities. There is a formal way to prove that, and for that you need to use this activation function.
If I use sine inverse, a sine hyperbolic, if I want like instead of 10 hyperbolic, if I use say sine hyperbolic, what will happen?
I don't know. That's a good question. In principle, you can do whatever you want. The notion of this, sorry, where is it? This ReLU thing comes from neurons because you have, let's say, 4 neurons attached to 1 neuron, and then you need to accumulate enough information to be able to trigger. So that's why they want to have something that looks like that. Now, as I said, there is ReLU, and then there is tanh-H. Can you guys, you can imagine how the tanh-H look like that, okay? Can you guys think why ReLU is the preferred over the tanh-H? Ernst was saying something about during the afterthought or something like that, right? So maybe I give you that to that. But it is an interesting question to me. Why people use ReLU more than tanh. Let me give you a hint. Is ReLU computationally more complicated than tanh, or vice versa? Simpler. So how many computational operations you need to build this function compared to the tanh? Fewer. So that means that people use ReLU essentially because it's cheaper, mostly because it's cheaper. Tanh are more expensive. And if you want to build a very deep neural net with tons of activation layers, that means you are going to use a lot of compute. But you can bypass that just by using something very cheap. Now, there is also other arguments that the ReLU produces real zeros, right? This is literally a zero, the mathematical zero, as opposed to a tanh that kind of doesn't produce exactly zero. So for instance, for image generation, where you want to have a pixel that is empty and nothing, those transitions are easy to generate when you have something like that. But if you want to sort of cook up a function that is kind of smooth, unless you have like a gigantic number of layers, you are going to generate something that is kind of, clunky. And, tanh is actually a better choice. So that's the reason why there is tanh in ReLUs in general. Right. Okay. Okay. Now, let's talk about auto differentiation. Because in my opinion, this is, beside the normalizing flows that I'm going to be talking about, this is my personal view. If you want to make a dent in the next upcoming years in research using AI, you need to embrace this concept of auto differentiation. If you are not using auto differentiation, the train is gone. Okay? You have to embrace auto differentiation. That's the most important thing. And I will try to elaborate why that's so important in this very simplistic neural net model. So as I said, this neural net is just this linear transform, activation function, and a nonlinear transform. And all these parameters inside of these red boxes are tunable parameters. So how do you tune parameters? Well, you have to move them, right? You have to basically shift them, and you shift them with the same trick that human has been doing this thing for centuries, a gradient. You have to define a gradient to move the parameters. Now, you will define this thing by having some objective function to minimize. So let's say that this output O1 can be connected, can be put inside of a function that you want to minimize, right? It's your objective function. We call that thing the loss function. And you want to compute a gradient of that function with respect to all these parameters. Now, this is a very simple neural net where you have, as you said, 10 plus 16 parameters. This is the most trivial neural net. Normally, people build a single neural net and it has order like 1 million parameters. So now imagine that you want to compute the gradient of millions of parameters out of this. So do your exercise to start doing your chain rule by hand, one by one, right? And of course, that's not practical. And so because it's not practical, people came up with this auto differentiation. When you launch that model, behind the scenes, there is an autograph. It's like a computational graph associated with this model. And that graph is capable to compute for you the gradients automatically. And that's to me, the most important thing ever. If you don't have that, there is no machine learning. sorry, not Gaussian processes, genetic algorithms, and why not? But if you don't have auto differentiation, you're essentially screwed, and you should not keep doing anything because life will be extremely difficult. So embrace this reality. And the reality is that when you write a code, you have to write any torch essentially with auto differentiation. If you don't do it, then yeah, it doesn't work. All right, so let's try to see how that works. Again, the symbol for collab. So let's go back to this, the same model that I started. Feed this tensor, okay? And let's pretend that this is the input tensor, and we want the model to go into these values. So let's define this Y tensor, and this is my training data. And notice that there is a batch of size 4. There is one example with its corresponding value. So there are 4 of them, right? So try to code up this, feed this X into the model so that you get the fake. I call fake because that's very useful for me to distinguish everything that comes from ML. And then let's try to compute, for instance, the root square mean error. So fake minus the true square and take a mean of that. So this will be my objective function. I want to minimize this function. So what you're going to do is you are going to call this function called backward, okay? And when you do this backward, now all of a sudden you should be able to have access to the gradients. And to check that there are gradients that are non-zero, you should try to compute, you should try to execute these lines here. So go ahead and convince yourself that something is coming out as gradients. Give you 15 seconds. Okay. Whatever it works, you need to have torch. Yeah. Nothing fancy. Anyone got stuck with this idea of trying to evaluate the gradients? Okay, I told you that auto differentiation is the most important thing. And one of the things is that normally when you cannot optimize a model, typically it means that your gradients got lost. And this is the way to check whether your gradients exist. It's a very important cross-check that your gradients exist. So you should be able to see an output that looks like this. Is that true for everyone? More or less? Do you see an output that the number doesn't have to be the same, but you should be able to see something very similar. So let's digest this thing a little bit. There is a for loop going from, to query the name and the parameters of the model. Yes, okay. So what you've seen here is essentially the first layer, okay? The weight matrix of the first layer. It has to be 2 by 4, right? And this is the weight of that more, you were asking me, Nick, about your numbers should be different from mine because this is instantiated randomly. And the gradients has to have the same at least size, right? Again, I want to make sure that you understand this step. All we are doing is to take the partial derivative of the loss with respect to each of these parameters. And what you've seen here is basically these values, sorted out like that. So this will be for the weight matrix. This will be for the bias of the first layer. Notice that there is nothing associated with the activation function because the activation function doesn't have parameters. So you go straight to the second layer that's supposed to have only two weight matrices, two values for the weight matrix and the gradients. And the bias should be only one because the output is one. Everyone okay with this?
Sequence,
Repeat what?
sequence, yeah.
The sequence of what I just said here. Okay, so this is the weight. Okay, maybe let me try to help you out here. So recall that our model is 4-2. So 4 input to 2 outputs. So that means that the weight matrix is 2 by 4 and the bias is 2, right? And this guy here is 2 to 1. Therefore, the weight matrix is 1 by 2 and the bias is 1. All right. Then here I see the weight matrix and these values are the gradients. Basically, the derivative of the loss, which I just defined here. This is a scalar function, and I'm just trying to compute the partial derivative with respect to each of these entries, and that value is these values for the weight matrix. Then I can look at for the bias vector, these two inner. This is the values of the bias vector, this is the derivative, the gradient, sorry. And then this is the corresponding one for the second layer. And it's ordered like 0, then 2, because 1 is labeled for the activation function, but it doesn't play any role. Any further? Yeah, go ahead.
What's theta? Sorry, we're right behind each other. Go ahead. What's theta I here?
Theta I are labeled for all these parameters. So here, this is the weight matrix for the first layer. This is the bias. Recall we said 10 parameters, right, for the first layer. 2 by 4 plus 2. And theta I are just basically a label for each of these entries. And I'm just taking the derivative with respect to each of these entries and just displaying it here. Yeah.
I have two questions. One, to take a derivative or a gradient, don't you need 2 points?
Don't you what?
You need 2 points. Like, I have 1 point here, 1 point here. I need a
Good question.
there.
Good question. That is taking the derivative using finite differences, which you can do. But the magic of the autograph is that you can know analytically all the function. So you can take exactly the derivative. The autograph is designed to compute the gradient exactly.
The autograph is in the loss function.
The autograph, you don't see it, is behind the scenes of here.
So it's another one of these randomly generated numbers.
No. The autograph is a computational representation behind the scenes that is keeping track of what you build here. So when you do backward, it instructs to go and compute the exact derivatives, the exact partial derivatives of the loss function with respect to every single parameter of the model.
Oh, within trying to get those parameters to your training data.
No, there is, well, yes, so the gradient, in order to compute the gradient, I need to feed some data.
And you kind of do have 2 points to compute a slope, I guess, or a gradient, I guess. It's trying to get 2 somewhere, so it knows.
Yes, okay, sorry, I meant, yeah, I understand now what you're saying, yeah.
Well, yeah. And then I guess my second question right before yours is, like if you go to, I guess, slide 17 or something, I thought we were supposed to have,
I don't know which 17. Yeah.
I guess go back one, that one. So I see the 4 by 2 for our weights, and then I see the 2, like when in this, when we name all the parameters. So our weights 2 by 4, and then bias is 1 by 2. But then down below for the, I guess.
This is wrong. This is wrong, right?
Okay.
This, yes, sorry. Thank you for catching up. This is wrong. I should not have this, and I should not have this.
It should be a 2 by 1 and then
1 by 2.
and then a 1.
1 by 2 and a 1. Yes. Sorry about that. Thank you for picking up.
So we chose in this instance Ange, but what if we had chosen ReLU or like more like a piecewise kind of function? Does that have an effect on our ability to calculate gradients?
Oh, yes. That's a good question because in principle, Hansch is differentiable everywhere. That's why you can calculate exactly. but a ReLU that has that kink is not. So what people figure out is that, okay, the derivative is not, it doesn't exist exactly at the value at 0. So they set the gradient to be 0. So by default, the derivative at that point is 0.
That's not right.
No, they define it to be 0 because it doesn't exist, because the derivative at the kink is not defined. The function is not analytic.
So but they defined it. It's not
Yeah.
definable, but they defined it.
They put it 0. So the idea is that the chances that you get to that exact 0 is not always, it doesn't happen that often.
But if it does, then
You will return 0.
Okay.
But then, again, it comes from the complexity. Do you want to have a deep neural net that is extremely cost because it's a bunch of tanh that is very pricey versus having just ReLUs that are very cheap and ultimately heating up the earth by doing machine learning? Yeah.
Having a gradient of 0 doesn't mean that if we land into that point, we are stuck there.
No, because recall that it's a gradient of all the parameters, right? So everything is moving. So it's not going to be stuck there.
Because it's just that parameter.
Yeah, but okay, recall that the gradient, putting 0 will basically put zeros to other, the gradient for other parameters, right? The one that are above in the layers.
Yes.
Yes, but I think that you have to get exactly to that 0.
Yes, you have to get exactly to that 0.
Yeah. We're going to do an exercise where you can swap tanh H and ReLU to see by your eyes, what is it? Okay. Let's see if I can finish to where I wanted to go, but maybe not. It's okay, this is fun. All right, okay, so now I need to tell you how to optimize. So I just told you how to define the gradients, right? So this is your training data. I want to take the gradients. And once I have the gradients, I want to move the parameters of the neural net where the loss is minimized. So how do I do that? Or how people do this? So the first thing is that you have to define an optimizer. And the optimizer comes with a name called Adam. Then I forgot what they stand for. There are other versions of the Adam. You can Google towards Adam and it tells you exactly the recipe of Adam. Is very simple, nothing sophisticated. There is this parameter learning rate. That's very important. If you make it too small, you can't learn. If you make it too big, then everything is crazy. And then if you're an expert, then you use hyper optimization and then you figure out what's the best learning rate. But for time being, for this example, let's try to take this. So the first thing that you have to always remember is to write this line, optimizer 0 grad. I have seen my collaborators and students and why not, this stuff doesn't work. This is so stupid. I waste an entire day of work and this doesn't train. And I just look at the code and this line is not present. If you don't have that line, everything sucks, okay? Why is that? The reason is that every time that you move the parameters, you need to wipe out the gradient. You need to put them to 0. If you don't do it, next time that you add, you compute the gradient, it will be added and added again. And so the gradient becomes completely crazy every time that you call backward. That's why you have to wipe it out. Okay, so learn that lesson. First, wipe it out. Evaluate the model, compute the loss, compute the gradient, and optimize step. That's it. And this optimizer, notice that the optimizer knows the parameters of the model. So as soon as you set step, it will go and optimize the model. Okay. So what I'm going to ask you, because this is CEO, you should go and try to execute this line once and see and print the output of fake. The output of fake, if the weights and biases has changed, that means that that output fake has to change over and over. You can also change loss because you see in the loss, only fake should change. Y is fixed. So you should be able to see that the loss changes every time that you execute this line of code. We'll give you 10 seconds to try that out. Does it work? Do you guys see that the loss is changing? Right?
Does that mean that it's finding another optimal point?
Yes. So if things make sense, the value of the loss should decrease.
Yeah.
Numerically. You should start seeing that every time that you run it, the loss decreases. No? Well,
How is it remembering to set optimizer to 0? How is it like it's getting better? But how is it remembering the previous step?
Iterate.
so I'm just asking you to just execute this thing only once, right? Or maybe twice, just shift enter, and print the loss every time that you enter. So you should see that the loss is going down.
Yeah.
That's simply because this line here is moving the parameters in the direction where the loss decreases. So you make a step, and now your loss should be smaller. Now the gradient is in this direction, and it should be smaller, and so on and so forth.
Oh, I have run this command twice. Now it seems to be increasing.
Yes, it can happen. I keep doing it for a while until midnight. No, I'm joking. That's why you will put here a for loop, because that's why we can use for loops. And you should be able to plot, and the behavior of the loss at the beginning is kind of typically will go down really quick, but sometimes it can go up, but it will go down, and it will go up, and it will go down. And how to handle this mess is another story, okay? But in general, it will keep going down because behind the scenes of this Adam is clever to make sure that things will keep going down. So of course, I'm not asking you to stay until midnight, pressing shift enter until you converge. You put a loop, and then you can do that. But at least you get the mechanics, at least in one of the loops. Everyone all good with this? Any questions? No questions? All good? Everything is super trivial? Okay. Okay. So I'm supposed to have stopped here. I wanted to ask you the question about ReLU. We already asked the question. Because how should I? Oh, the plan that I had was, do you have any questions? If you don't have any, I have some few questions. Do you have any more questions? Yeah.
So say I want to change the neural network to 2 input, 1 output. And I know how to do that. My question is, how can I want to plot the output of the network.
Sorry, what's the architecture that I can just see? So the linear layer is what?
It doesn't really matter. So I want you to plot the network, like the output of the network, basically.
Oh, okay, yeah.
How can I do that?
So let's see. Here, for instance, you fed 4 examples. And then when you feed this thing into the model, this output should have 4 rows and 1 column. And each of those 4 corresponds to each of these inputs. Any question is okay. You know, if you're stuck here, then everything else is going to suck very badly. So tell me if this is okay.
Should the loss decrease asymptotically to zero or?
No, it doesn't have to go to zero because if your model is extremely deep, then you can make essentially the neural net to pass through all the points. Right? In that case, it will be zero. It can also be the case that your model is too restrictive and incapable to go to all the noise. People don't want to go over all the noise because that would be what people call overfitting. And so there are techniques to regulate that so that when you're kind of optimizing the neural net, you don't go to that stage where the model is passing through all the points. So there is something called cross-validation, where people partition the data into two samples, the training sample and the validation sample. And so what happens is that at the beginning, you have the training sample, let's say, go down, okay? And then there is a validation sample, maybe here, that is also going down. And eventually, the validation sample is going to up. And then they define a region to stop so that you can see, it's kind of the trade-off so that you don't overfit. That's, for instance, the technique that NMPDF, in the context of pattern densities, they use that. So whether you want to overfit or not, that's on you. Your problem, you decide how to do it. But there is no, PyTorch doesn't dictate to you, stop. You define the stopping criteria. All right. Yes.
Before we go on. So you said it would be, you could print the fake X or fake, print fake. And then we could also print loss. Loss should be going down, and that's true. But if I run this, I ran this like 100 times, I wanted to see what it looked like. I expected fake then to approach Y, what we gave it. And I guess for one example, that one, they're all like very similar to each other. They're all like pretty much the same number. And that number was going up. It was going up, 6, 7, 8, 9, 10. I expected the top one to stay 10, and then the lower 3 to then continue increasing, but they all just kept increasing past 10. And now they're all increasing up into the end. I don't know. They ended up as 13. Like 13, 13, 13, 13. I expected it to be 10, 13, 13, 13 until it reached 20 or something along those lines.
Right. Yeah.
It didn't do that. How many times do you need to run this?
We will try a better example, at least the one that it will work. But what you're describing something is more similar to saying, do I have enough complexity to match that data? That's one thing that you need to have. And in machine learning, there is this problem in general that imagine that you want to go to your neighbor, and you have two ways of transportation. One is a space shuttle, and the other one is your feet. Clearly, one is useful, the other one is not. Both are forms of transportation. In machine learning, it's very difficult to disentangle that. So people start putting a bunch of layers arbitrarily at the expense of no notion whether it's a rocket ship or it's just your flip-flops. So you have to decide when is good enough. And that's essentially very case-by-case model depending. It depends on your objective. I will tell you some problems are very, very subjective to that. Like your decision-making about how complex your neural net is. Other problems are not. The normalizing function I'm going to tell you is not too much about that. Hopefully, otherwise I will be here forever. Okay. Any more questions? Okay. I have like 10 minutes more. All right. Where I was. Okay, so that brings me to the exercise session. And I think that would be a good place to try to use the skill set that you learned today. Take this example. This is just a sine function with a frequency of 4. So it should be something like this, between 0 and pi. Okay? And try to tune it. So first you have to decide what kind of neural net I need. So let's imagine what should be the architecture. So what should be the first integer here? At least that one is deterministic. Anyone?
10.
Let's say 10. Any other number? So I want to build a model, right? And then sequential. So the first linear layer for that problem is at 10. It's 10 real, reasonable. 100 times 100. Okay, so another option, 100 times 100.
Oh. 10 by 2. I even needed two numbers. I was just putting
Okay.
one, at least one.
Let me give you a tip. How many
You have other points there, so you need at least.
How many examples do you think you have here? 1 or 100?
100.
You have 100 examples, right? So the model architecture should start with 100, or what should be the starting point here? Yeah.
50 by 2.
You want to mimic a one-dimensional function that receives x and outputs y. It's y. It's just 1. So this should be 1, right? Sorry, comma, something. You can go from 1 to whatever you want, right? You will have your tangent h here. You can have more layers. So let's the last one, the last linear. It has to go to something too. 1. Okay, that's the hint. Build a model to reproduce a sine function, receives x and returns y. Make your life, you can play here with tanh h versus ReLU to see how it works. Okay, I give you a few minutes. And after that, I will show you my version, see how it works. Oh, you recall that your question about that, the loss goes up. So you can see here, this is an example of what I run. So the loss goes down, then it goes up, goes down, goes up. So this is what you will see just by pressing one by one. But you can put it in a loop and plot it, and then you will see something like this. So at least my version is successful. The true and the fake matches. So I know how to tune a sine function. Tell me if anyone needs any help. That I'm stuck. I don't know. There is no shame in this.
I have no idea what this is. Why 100 or 1 versus anything else?
So this is a function, right? That should receive an input and output, and you want that thing to match that problem, f of x, sine of 4x. So the input should be x, should be one-dimensional.
Okay.
And the output is also one-dimensional, sine.
So then the 100 there. So what is this lin space function?
So that creates, so lin space, okay, I didn't say what's lin space. Apologies for that. Lin space, it will create an array equally separated between 0 and pi, and it will be 100 of them equally separated. It will give you a tensor, which is 100 points. 100 points. And then I evaluate the sine values there. So I have now 100 examples, right? Now, be careful with one thing. If you pass this x to your model, it will fail. You have to transpose it so that it becomes like a row vector with a bunch of 100 examples. Otherwise, it won't work. Recall the two nodes? Yes. I'm going to go in this order. Yeah. Yes.
Like 10H provides some Y out of whatever goes in here, in this case.
Yeah,
They'll
that
give it an X, if I want it to just be like, I want it Y equals X.
Oh, I don't know, let me.
Well, I don't know that example because I just made it up. I just want to show the gradient can be computed.
Yeah.
Whether it works or not, I don't know.
Model.
Oh.
Your entry.
No. I think in the example I put.
Isn't it like
Like
a-
our 4 rows.
Yeah.
Rows of you mean and you know 4 tensors
Well,
and then the
my
other-
idea
the one that
is if I give it like
So
two.
in principle, that should match.
All equal to each other.
No, the output is only one.
So I was thinking,
Therefore,
it already
it's not.
gave 10H.
Dimensional.
Maybe I could-
In principle, you should have.
I just like trying to
It's
fix my
not that interesting. It was just for the purpose of showing the grade.
Cosine H and then sine H.
Here
or
this,
10H.
Well, you need
Yeah,
to bound.
X is one, right?
Yeah.
So this can be any number.
Whatever you want. Any
So-
number,
Any
yeah.
number if you want.
Point that you
But
can use it.
this
Interim
this
bound.
number should match.
Yeah, exactly.
Yes, so here we are defining X and Y, then we need to like
The middle you can.
do all of this again.
That's why it's an activation.
Yes, so the.
Yeah.
Like that.
Where the.
Yeah, over one.
So you can figure it. Like a.
10H doesn't go to infinity. Doesn't end at pi, does it?
I think
Oh.
that you can do the backward.
Input and map to the domain of the activation.
Yeah, I try it out based on what I said. I don't know. I don't digest activation. X is the activation. Do you have any questions?
These.
Yeah, but I think it's the same one.
If I have an input like 100.
If I want to
From
activate
one
your-
space to.
I mean, a number with
Usually
here,
you scale the 100 down between my.
Shouldn't be already one.
Depends on your problem. So if you're solving this, that should be one.
Like, what if you're working with?
Okay, but-
X doesn't have to be pi.
Because this
it's pi.
You're saying I want to mimic a
I mean,
function.
obviously, you're not gonna use.
It's basically R1 to R1.
okay.
So now we put
You have to.
whatever happens after that, that could be anything. Then at the end,
I don't know.
Yes. Yeah, output.
Yeah, already, was already.
Whatever you want.
Okay. So.
Well, no, okay, that's the domain
Is that
of
like a
function,
little
but
number?
the domain of the
Or the
activation
number of,
function is specified within.
Some people said that
The back and
layers captures
whatever's going on inside torch.
and
10H is automatic.
the number of neurons, which is basically what you
Bounded, I would assume.
capture how good you want to buy.
Sine.
No,
So-
because tangent.
That's our function. That's the only. To be honest,
Yeah,
you were
Extension
one
book of.
Yeah, okay.
and
then
see, so there are other algorithms. that
Not
can-
bound, not bounded to some X, Y, but bounded to
Basically, I want
finite.
Yeah,
I
the
see,
Y
I
value.
see.
try to figure out what is minimal setup that is.
How much does it know? It's
Yeah.
Give it like.
I will play around, but.
Oh, I don't know.
I
Technically
don't know.
finite.
Yeah, I mean, you don't need the, make a sign.
Sign except for active.
Wait, what?
Yeah.
Yeah, I got the same.
I think this example that I didn't.
Yeah.
Okay, yeah.
So it has its
I mean,
Having
your space.
Yeah, it's just a sign, so maybe.
Two, it's small.
Yeah.
Oh, yeah.
Okay.
Then just technically.
I mean, in principle, if you have only
Exactly.
one linear layer, then.
There's just a bounded.
That- yeah,
Oh, okay.
I'm not sure if this.
Yeah, unfortunately, there is no good rule of thumb, other than just.
I mean, you
involve-
can press in, I don't know if it makes sense.
You use with
Yeah, exactly. Yeah, because you can see it from the outside, what's going on in the glance, so I guess.
Yeah.
Right up.
So read out.
Was the medicine before I.
That-
Right, you try this.
Already.
What?
Year 1 by x, blah, 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 blah. Linear x by.
Say it again.
But
Just.
already. Yeah, so this is the.
So I think the simplest thing is just to put x dot. If you put, so just create a new cell in between these two. Just click here and plus.
10 years?
Yeah, plus curve. Yeah, put x dot t.
You put the one.
Yeah. Try that, capital Y. Okay. Shift enter.
Wait, so what was he doing?
No, so
Yeah, okay.
so that you need to add like.
Try to do
For example.
-1.
Why?
Parentheses -1.
I asked Gemini and it's
The
been.
view,
Pass.
VIEU. Yeah, try that. Yeah,
Oh, you unsqueezed the Y. What did
now
I
it's
squeeze?
transpose.
Why?
Need to use this.
Unsqueeze.
Yeah, too. There are various functions like view, reshape,
Yeah, I asked Gemini
But
why
there's
it
a
didn't
third
work
one.
and it's been.
all of them achieve essentially the same thing. That you will reshape a tensor in a way that you want to feed it. Okay.
I don't know how no.
And then when.
I made an x
yeah.
and I did empty dot transpose.
So the transpose, I forgot to say how to write the transpose. So for x, you can type view -1, and that will, if x were something that looked like this, then this will look like. And you need to do this one because you want to feed to a model that receives one input at a time, right? There is view, there is reshape. And I forgot the other one. Okay, T2 works. Okay. Parenthesis, .t parenthesis apparently does the same thing.
This is what I found. The work.
It didn't work. Well, I have to write it to complaints.
I can show my version. Who has finished the exercise? 2 people, okay? Who didn't do the exercise? No, didn't do it, who are still working on the exercise.
Yeah, okay.
Oh, a lot of people, okay. Keep working.
We'll start flash.
Maybe. And I can show, it's my version. So how about this? I'll give you 10 more minutes. Then after that, I will show my version, how I did it, and then we go. I have still purchased. I didn't.
Good enough.
So,
But you, but.
But normally for
letting down to them. Because like, what are you making Python the pro? For example, you want to make the force with letters.
Yeah, you have it.
If you have that ready to start that, you should see them in this device.
I was thinking that maybe I could finish with this place.
there's some training.
Oh, maybe you can do statistics with your 100. Has it everything to ChatGPT? Statistics, how many slides?
Why?
Approximately, right?
Physics.
Yeah, just average it, right?
Your loss functions that I'm training. Quit training me. Would,
Right.
and as you want like the log in loss function.
No, it's not the log, so.
The code is wrong?
Yeah.
It's a few years ago, where I was doing share. That's about. I think just the steps. How if you.
Okay.
And if you. Increase too much. It's the problem.
Does. Why? No. That works. Why not? I haven't gotten stuff yet. ChatGPT is why it. That was a big ChatGPT.
Define the domain, right? The parameter value. Use X. Short one. It needs to be.
It's just your starting with. That is the first entry.
Yeah,
Of
yeah,
time.
yeah.
Uh,
No, but how many values I need to?
in this case, your X, that one.
Understand, but I think so I just need to.
Oh,
Yeah.
Oh, sorry, I just saw it.
Hey, you got it.
But then we use this,
Yes.
like, define the domain.
Yes.
I don't need.
No, you never use this, for that. All the parameters start random. And that is how you are playing here.
I just need.
No, I'm training.
Yes, but with the numbers,
Yeah, yeah, yeah.
step to step. That.
How's everything going? All done? Have finished? Okay. Some people think that has finished. You finished? Maybe. Okay. What are you trying to do?
think that it's the same as the line. So
Yeah, yeah.
It's like, so we do an explanation.
But is that model in you want to
Do that. Have it code down.
and use that? Right, because your input is a scalar. And your output is
So-
scalar. It should be 100.
Okay.
Otherwise not 100 on R1.
This is what I
It's
was.
because the hundred, the x-axis.
Those are the examples, so go to, do you have my slides?
Would we see the
Yeah.
I think you just approved. What you're interested in is the parameters.
Yeah.
So if you
Then
want
you
to.
can give that you have a function that you want to imitate this the sign of x. And then you have
Okay, thanks.
Yeah.
two layers with the linear part. in between.
That's weird.
But this is going to be a single.
It's that
I have
your model
than one example.
becomes a sine of x.
Like at this point, it.
Then I need to, I forgot.
Like-
I do the whole.
No. It's your object.
It's up
Yeah.
to you. I don't wanna cut you off now, but yeah, sorry.
Your model starts, your model is just
It's
like.
like, or otherwise, I don't know, later.
But truly,
I
it's
found
almost
some
a
presentation.
Sure.
Or there's Zoom, right?
It does something random in your data.
And when you feed that.
Yeah.
I mean, it doesn't do sign of 4x, okay?
Okay.
But you're train it, so.
Yeah.
So like, it becomes different, so what you're interested in.
Oh, yeah, I can't.
After.
Yeah. Usually letting a simple function with a neural network. Yeah. Left out lines.
To see if that it's working, you should just.
The noisy loss function.
Use the model. And see the. What
He's first neural net. Yeah, exactly. You know?
I don't know.
It's not meant to be great. No.
And you see that.
Yeah, that's super typical. You can sudden fall off and then, yeah. There's not even any validation data here.
Yeah.
So you're just training until you generalize, yeah, exactly. Until you see that you fit signs. Yeah. Fun. Yeah, collab is pretty cool.
So.
Now we need
Yeah.
to use this. later.
Yes.
Yeah.
Kind of nice that you don't have to like install much yourself.
Yeah, you could do live coding at this point, right? So,
The numbers.
have you heard of it? I have not. Yeah, vibe coding is generating usable code like ChatGPT effectively.
Doing anything.
Oh, that didn't work, so debug this, and okay, now it works, and never actually, literally never looked at the code itself. No, I mean, I've done. I did quite often. Like, there's some danger to that. I hear the problem, solve it. Yes.
Test it.
This should be 100.
Yes. So.
Yeah, that's
It's like.
In Jupyter notebook, you just have to reset it, like rerun it.
So maybe there's setting, but every time I like go in the Python in the script, I got.
You're like all I.
No, it's.
Yeah, see.
Yeah.
So it's deleted that, people that it also deleted that. Excellent.
Shapes up. Agree. Because you have 1,100, you give it 1.16.
Yeah, it's
I just say it.
Yes.
It would be. It's not like that.
This is just.
It should be standard. But it's not wrong, but not big.
And give you.
Just delete it, isn't it?
But you're starting with 1 and then you get in 16. Okay, so you should start 100 and go to 16 if you want.
Oh, okay,
Because you have 100 points here.
yes.
Okay.
This one.
Otherwise, things are crazy.
Yes.
So this comma is like initialization.
Oh, because I didn't copy over.
Okay, gradient.
Yeah, you have to
Yeah,
wipe it out.
oh, that's, yeah.
I included the optimizer thing to set it equal to 0, but I
I
didn't.
don't know if this doesn't just one pass. That's the best that you can do. But anyway,
Now I.
you should at
I
least,
need to plot it.
yes, you should at least plot what the model does after you train. I don't. See, it's like, I don't know.
If it is working.
The actual first test of whether or
Uh,
not.
I don't remember.
So I will show him an example.
You already have one.
Then
Because
I will make that example.
I'll try to copy, but I don't know.
I'm searching.
Yeah.
More.
I'm putting on.
Yeah.
Yeah, so I think it's detached, I don't know.
Values.
The tensor.
Oops.
Form is stored into.
Some successes and some.
Like a while ago. I look again on my door. Is there any way I can get it, or I can make it myself?
Oh, but you
Okay,
have,
thank you.
you have that.
I do, I think that the last one.
Oh, okay.
See, something
Yeah, like
detached from our plot.
Yeah. You can, like, in the plot command, you can call it. But like, you can also run it.
No, it's not ChatGPT. I'm sure the ChatGPT.
Not yet. I was trying to do that. Let's see if we can.
I only respect. Yeah, it's that, you see, mine goes from 100 and then keep it going down and down and down.
So it's already at I can increase the.
That's like not terrible.
Yeah, I can't actually see.
No. Plot in the model.
Maybe, let me
It's my sign.
show you my verse, you can compare what I did, okay? Alright, guys, I think, I need to show my version so that we can leave the place. I've seen some successes, some other trials. It seems more difficult to train a sign function, but if you can manage to train a sign function, you have succeed your task. Let me show you what I did. Assuming I have this thing. Let me see. Okay. You see my screen? Yeah. Is this too small or should maybe I will do something like this? Okay. All right. This is the model that I use. 120, 2020, 21. Right? This is the data. So you should have that. Don't pay attention to this one. I have the atom. The weight decay is something else that you can use, but I think is, did I ask you to use 0.04 for the learning rate?
Yeah.
Yes. Okay. So same thing, right? Let me just run my notebook. It's really quick. Okay, I use 5,000 epochs. So let's see if I know what I'm talking about. I have to wipe out the gradients. Step 1. Step 2, evaluate the model with the X value. So I use view -1,1 to convert the examples into this format, right? Then I flatten it out because I want to go back to the raw version so that I can construct the residual and compute the loss. Any questions in this piece of the code as it stands? Is this the same thing that you have, or do you have something different from baselines? The fake minus square sum.
In a different order, but yeah.
You don't have to flatten. So let's think about what happened here. So this guy now is a row vector, right? Because X, I can show you just a little bit up. X is an array, actually, I can show you. Okay, hold on. I can show you here. If I type X, it looks like this. So this is a row. Even though it has multiple rows here, It's technically one gigantic row. You see, I can see that thing because there is only one curly bracket here and only one curly bracket here. So I know that is a row. Now, if I type view minus 1, 1, then it looks like this. And now this is a column vector. So I have 2 here, right? And down there would be 2. Okay. Did you guys got that part? Recall what I said, that you need to evaluate the model as a batch mode, multi-evaluation. And this is the way to tell the multi-evaluation. Okay. You remove this. So that's this guy here, and I feed to the model. When I feed it, it's going to give me a row vector or a column vector. It's only 2 options. Try it out. Huh? No, it will give you a column. It will give you a column. And then when I flatten it, I will get a row vector again. Because I want to be able to compare this fake and this Y on the same footing, same shape. So fake minus Y, that's all I'm doing. I square it and I sum them. I could take the mean, it doesn't really matter. Okay, you can take the mean or the sum. That's an equally valid loss function. I do these extra tricks because I want to sort of, access the loss. So this detach allows you to basically remove that quantity out of the computational graph. Usually you need to do that, otherwise it will throw you an error. I want to feed into a CPU, back to the CPU world, converting to NumPy, and extra steps so that I can append here in my loss array. I want to sort of construct an array of the loss. You can ignore this. Do you guys understand up to this part? Any questions there? No questions? All right, and then I'm going to sort of see the outputs every 100 epochs and kind of plot the loss and plot the real and the fake every 100 epochs. And that's all I'm doing here. So let's try it out. And look like that. Okay, you guys didn't get to that, but I'll share the code and post the cell so that you can analyze. And maybe if you have more questions tomorrow, you can ask me about that. Notice that this stuff is a little bit crazy at the end. And the reason why it goes crazy is because when you go to very small values of the loss, there is this parameter called learning rate. And the learning rate is kind of like a factor to multiply the gradient to move. So we are basically using the same factor with the gradient to move the parameters. But as you go to lower and lower values of the loss, the tiny changes that it was occurring at the beginning becomes too big at the end. And therefore you can sort of move the neural net too fast. And so there is something called scheduler that you can actually use. And what this does is essentially to try to decrease the learning rate as you progress in the learning. So that you can, so you have to instantiate like this. And then somewhere here in the optimize step, you just write this line. So let's see, how does it work? Sorry, this is the optimized version. Let me execute it again. So what you will notice is that now the loss function somehow converges into very nice and clean-ish thing, and then it plateaus, and it doesn't move. Okay, I will send you this piece of code. If you are tomorrow we are going to do a little bit more engineering around MLs. I suggest you to get acquainted with this. I think this part is always confusing. The view, the -1 and 1, it was very confusing for me. In fact, I get confused every time that I start doing this over and over. But there is not much to learn about this. It's just two ways of operating. And with that, I think that we should close at this point and see you tomorrow, guys.
Good. Thank you, Bob.
We have questions, but I'll just go ahead and ask.
Oh, yeah, go ahead.
I guess I sort of think I know why, but why,